Okay. I think this cut off. Okay. So now we have our observed and expected tables, and we can calculate our chi-squared test statistic as shown. And this is a one-sided test, so we can compute, if we wish, the p-value for our test statistic and find that it is greater than 0.05. So the p-value was greater than our test statistic, so we would not reject the model. So it is a good model. Okay, and then we got into the theory for what we're doing here. So H0 is a multinomial distribution with cell probabilities P1 to Pm parameterized possibly by theta. And our alternative is that we have some other multinomial distribution. So capital Omega is essentially all P1, Pm, which are non-negative numbers between 0 and 1 that sum up to 1. So that is some open set in Rm, and our set of p thetas for theta in this open set omega naught is a subset of capital Omega. And then our lambda here is the ratio of the max of the likelihoods for theta and omega naught versus our P1 to Pm in capital Omega. So the numerator is exactly the likelihood of our PIs, where they're parameterized by the MLE, and the denominator is just is just exactly the p hats. So the MLE for the p's. So that's just by definition. These p hats are, the MLE for the p's are xi over n. If you think about it, what else could it be? But if you'd like to see a proof, it's a little complicated actually, because there's a constraint with the xi's summing up to n, so you have to use Lagrange multipliers to do this, but you can read about that in the book if you'd like. We get xi is n pi hat, and I just want to note that the pi hats approach in probability the pi thetas, and that follows by consistency of MLE. So now our generalized likelihood ratio, we can do some algebra simplifications, and what you get down to is this expression. So this expression here is something that you could calculate, but it turns out it's simpler to calculate an approximation of this, which is given in green here, OI minus EI quantity squared over 2EI, and the 2's cancel there, so you end up with exactly the chi-squared statistic. So now we have minus 2 log lambda is this chi-squared statistic, and if you remember from last time, we saw that minus 2 log lambda asymptotically is a chi-squared with dimension capital Omega minus dimension little omega naught, and that is dimension m minus 1 minus k. So we get n minus 1 minus k. Assumptions of the goodness of fit are, well, you have a categorical variable, so your box is a multinomial distribution. The tickets in your box are independent because, just think about, for example, binomial. Binomial is a sum of independent trials, and each ticket is a trial. You're drawing a sample with replacement. If you are doing a simple random sample and you have a large sample size, we're friends, that's going to be fine. And for large, you need a large n because for this to have a good approximation of chi-square distribution, large n can be expressed as the expected values, the EIs, which are NPI. Most of them need to be greater than 5. If you have many of them that are less than 5, that means that some of your PIs are going to be small, and if the PIs are small, they're not going to, your XIs won't be well approximated by a normal distribution, which is something that is only true for binomial. Binomial is only well approximated by normal when your P's